First of all, I welcome all the students and the participants who are attending this live lecture. See this, in this today's live lecture we shall study the comparison test for convergence at infinity. See this is very important. ऋतुजा काळदाते, प्रीति बिराजदार, comparison test for convergence at infinity. Actually this is the lecture number 27. Now we have to use the comparison test for convergence at infinity, but we know that we have defined the concept of improper integral. Range of integral is infinite, means lower limit is a, upper limit is infinity. So the domain of x is a to infinity, so the range is also infinity. So these are the improper integral. In particular cases, range is infinity. Range is infinity means one of the limit, at least one of the limit must be infinity. So such types of integral are called as a range of the infinity. So also we have defined the convergence at the infinity, means at the right end if this limit exists. Also we have studied the convergence at the left end, means minus infinity if this limit exists, means replace this minus infinity by capital X and take the limit as x tends to minus infinity. If this limit exists, then we can say that the given integral is convergent, otherwise divergent. Similarly, this is the convergent at both ends, minus infinity to plus infinity, means it is infinity at both ends. So limit x tends to 0 minus infinity, limit y tends to plus infinity, integral from x to y f dx is said. If this limit exists, then we can say that the given integral is convergent, otherwise it is a divergent. So now we shall discuss the comparison test. Now see this comparison test. Before we know that the comparison test for convergence. 1 minute. Comparison tests for convergence at infinity. We know that by the definition of the convergence at infinity is, how we can write, integral from a to infinity f dx. If this integral is said to be convergent if limit capital X tends to infinity a to x f dx. If this limit exists, then we can say that given integral is convergent. If the limit exists and it is a finite, then the given integral is convergent. This is the definition where the function f is supposed to be bounded and integrable in closed interval a comma x for every x greater than or equals to a. See, this is the condition which we have studied in this section, that is improper integral having infinite range. So, already we have defined. Now, we have to study one theorem, that is a comparison theorem, which we have to discuss here. So, the theorem first, actually this is a theorem 3 from this chapter. In this chapter, the statement of the theorem is, what is the statement of the theorem? A necessary and sufficient condition for the convergence of integral from a to infinity f dx, where f is a positive in closed interval a comma f, is that a positive number is that there exists a positive number capital M independent of x such that integral from a to x f dx, which is less than m, for every capital X is greater than or equals to a. Say this, a necessary and sufficient, this is the statement of the theorem, necessary and sufficient condition that for the convergence of integral from a to infinity x dx, where f is a positive in closed interval a to x, is that there exists a positive integer m, capital M, which is independent on capital X, such that integral from a to capital X f dx, which is less than m. If this condition satisfies, then we can say that the given integral is convergent. Then we can say that given integral is convergent. This is a very simple theorem. So, I can write the proof. See this, the integral from a to infinity f dx is said to be convergent if, what we can say, that if integral from a to infinity f dx, which is equals to limit capital X tends to infinity, integral from a to capital X f dx, but given that f is a positive, but given that what we have given? We have given the function, see this, in the integral f is a positive in ax. So, given that f is positive in closed interval a comma x, the positive function, therefore, the positive function of x we get integral from a to x f dx is monotonic increasing as x increases. See this, but we have given that f is a positive in closed interval a to infinity. Now in the range a to infinity, the values of x are going on increasing up to infinity. So we can say that the function integral from a to x f dx is also monotonic increasing as x increases, as well as and will therefore to a finite limit because we have said that if this is a convergent, then the given integral, given limit has a finite. So we can say that due to this finite limit, it has some particular value, and due to some particular value we can say that it is bounded, and will therefore to a finite limit if and only if it is a bounded. It is a bounded above. Finite limit कधी येऊ शकतं? When it is a bounded above. Therefore the function is monotonic increasing and bounded above. So there exists. Therefore we can say that there exists a positive number according to the definition of the monotony increasing and bounded above. There exists a positive number capital M independent of x such that integral from a to x f dx, which is less than m for all capital X is greater than or equals to a, and hence proved अशा पद्धतीने हा थेरम प्रूव्ह होतो. खूप सिंपल थेरम आहे. परत एकदा मी थेरमची प्रूफ सांगतो. अ नेसेसरी अँड सफिशियंट कंडिशन फॉर द कॉन्व्हर्जन्स ऑफ इंटिग्रल फ्रॉम ए टू इन्फिनिटी एफ dx where f is a positive in closed interval a comma x is that there exists a positive number n independent of x such that integral from a to x f dx which is less than m. Means अगर इंटीग्रेशन कॉन्वर्जेंट है, given improper integral is convergent, then we can write integral from a to x f dx which is less than m. आता याच्या कॉन्व्हर्स, याचा अपोजिट, कारण नेसेसरी अँड सफिशियंट कंडिशन, ॲक्च्युअली वी हॅव गिवन नेसेसरी अँड सफिशियंट कंडिशन. That means we have to suppose this. In the second case we have to suppose this and we have to prove the convergence. But according to this supposition we can definitely say that integral of this a to x f dx is less than m and x tends to infinity. So we can say the convergent. Now suppose the first part. The integral from a to f dx is said to be convergent. That means integral from a to infinity x dx which is equals to limit x tends to infinity a to x f dx exist. अगर convergent होता है तो ये limit exist होता है and having the finite limit. But given that f is a positive in closed interval x a comma x according to the theorem, f is a positive in that interval that is closed interval a to x. अगर फंक्शन पॉजिटिव है So we can say that this integral is monotonic increasing. This integral is monotonic increasing as x increases, and it is a finite limit. So we can say that it is a bounded above. It has a finite limit. Finite limit means it has a particular boundary. We get some particular result of the limit, and function is monotonic increasing. Then definitely we can say that it is a bounded above. That means this integral having a value sum which is a bounded above. So there exists a positive integer m according to the definition of the bounded above and monotonic increasing. There exists a positive number m which is independent of f such that integral from a to x f dx which is less than m, less than or equals to m. इथं लेस दॅन एम म्हणण्याऐवजी लेस दॅन ऑर इक्वल्स टू एम. काय दिले पास थेरमच्या स्टेटमेंटमध्ये काय दिले पाहू. ओके, लेस दॅन एम, ठीक आहे, विच इज अ लेस दॅन एम अँड हेन्स प्रूव्ड. आता कॉन्व्हर्सली इथं ॲक्च्युअली कॉन्व्हर्सलीचा पार्ट घ्यायची गरज नाही आहे. व्हॉट इज द कॉन्व्हर्सली? इफ इंटिग्रल फ्रॉम ए टू एक्स एफ डी एक्स इज लेस दॅन एम, देन integral from a to infinity is convergent. Definitely we can say that the value of this integral is less than m, so it is a convergent. त्यामुळं तेवढं डीपची सेकंडची गरज नाही आहे. Now we shall discuss the theorem number next. Comparison test first. Okay, now we shall discuss the comparison test first. Comparison test first. As like previous chapter which we have studied, the comparison test, comparison of two integral, comparison test first, which is the comparison of two integrals. Actually comparison test first is also one type of a theorem, so we can write it is a theorem number 4. Suppose we can write theorem number 4. Okay, actually it is the comparison of two different functions. Statement, write down the statement. If f and g are positive functions and f of x is less than g of x, less than or equals to g of x for all x in closed interval a comma x, then prove that first integral from a to infinity f dx converges if integral from a to infinity g dx converges. See this, student, now you tell me. Actually we have already seen this type of a theorem. We have already seen this type of a theorem. Now you tell me what is the difference between that theorem and this theorem. Already we have seen one theorem, this comparison test first. But what is the difference between that theorem and this theorem? You have to write in the chat box. Pooja Gulbile, Ajit Warwatte, Sumit Thoke, Prathamesh Salunke, Darshan Gore. Now you tell me. And second condition which we have to prove, integral from a to infinity g dx diverges if integral from a to infinity f dx diverges. सेम थेरम आहे. अगोदर ज्या पद्धतीने ऑलरेडी वी हॅव प्रूव्ड दिस थेरम, बट इन दॅट थेरम द रेंज was finite. In this case, integral from a to infinity, but in that case, integral from a to b. That means, in this theorem and in the previous theorem, there is a main difference is that, in this case, the range is infinite, means a to infinity, and in that case, the range was finite, means a to b. एवढाच फरक आहे. अगोदरच्या थेरम मध्ये ए टू बी असत होता, आता या थेरम मध्ये ए टू इन्फिनिटी आहे. दोन्हीत एवढाच फरक आहे, फायनाइट आणि इनफायनाइट. इथं ए टू बी असण्याऐवजी ए टू इन्फिनिटी आहे. सो थेरमची प्रूफ करण्याची प्रोसिजर एकदम सेम आहे, काहीच बदल नाही. जसं अगोदरचा थेरम प्रूफ केला ना, तोच थेरम इथं वापरायचा आहे. प्रूफ already we have proved the comparison test for finite range. Already we have proved. In this case, the infinite range. हाँ बरोबर आहे, finite limit or finite range म्हणा. Let f and g are the bounded and integrable functions in closed interval a comma capital X. Capital X is greater than a. Suppose that actually we have to prove this function, but in the given condition f and g are the positive functions such that f of x is less than or equals to g of x. Then we have to prove that f converges if g converges. Directly we can say, because f is less than g, that means if g is convergent, then f is also convergent. तुम्हाला इथं डायरेक्ट सांगता येतं f हा g पेक्षा लहान आहे, मग f जर कॉन्व्हर्जंट असेल तर त्याच्यापेक्षा लहान असलेला फंक्शन सुद्धा कॉन्व्हर्जंट होतो. दिस इज इजी. हां, but here we have to suppose that f and g are the bounded and integrable functions in closed interval a comma x. Given that what we have given, f and g are positive functions. We have given f and g are positive function, and also we have given f of x is less than or equals to g of x for all x belongs to closed interval a comma x. If f is less than or equals to g of x and both are the positive function, then we can write this implies that integral over a to x f dx, or we can write f of x dx, which is less than or equals to integral from a to x g of x dx. Because we know that f and g are the positive bounded and integrable function, f and g are positive such that f of x is less than or equals to g of x, then definitely we can say that integral of f of x is less than or equals to g of x. Suppose this is equation number 1. Now, number first, we have to prove the first condition. Let integral from a to infinity g of x dx be convergent. See this, according to the first condition, what we have given, if g of x dx convergent, म्हणजे integral from a to infinity g of x dx convergent. So, according to the first theorem, therefore, there exists a positive number m such that, see this, according to this theorem, according to the first theorem, there exists a positive number m such that integral of a to x g of x dx, which is less than m, such that x is greater than a. This condition satisfied. आता पहा, integral from a to x g of x dx is less than m, but f of x, integral from a to x f of x dx is less than this, means it is also less than m. So from 1 we get integral from a to x f dx or f of x dx, we can write, which is less than m. Then by the comparison theorem, x is greater than or equals to a. But by the theorem number 3, if this is less than m, then we can say that, but by the theorem 3, integral from a to infinity f dx is convergent. This proves the first part. This proves the first part. At the second part, now we shall prove the second part. तो पण खूप simple आहे. Actually what we have given in the second part, see this. Second part मध्ये काय दिले पहा. If g integral from a to infinity g dx diverges, g diverges असेल, प्रूव्ह करायचे. इफ सेकंड कंडिशन मध्ये गिवन काय अगोदर विचार करू. इन द सेकंड कंडिशन वी हॅव गिवन integral from a to infinity f dx diverges, then we have to prove integral from a to infinity g dx diverges. See this. Now see this equation number 1. We know that according to the second condition, integral from a to infinity f dx diverges. That means integral from a to capital X f dx diverges. If this diverges, then g of x is greater than this function. So definitely we can say that if this f goes to infinity, then g is greater than f. Then definitely we can say that g also goes to infinity. That means g is divergent. Now second, if integral from a to infinity f dx is divergent, then the positive function, integral from a to x f dx is not bounded above. Divergent means which is not bounded above. Therefore, this implies that from 1 it is not bounded above. Therefore, from 1 integral from a to x g dx also not bounded above, because f is less than g, f is not bounded above. So G is also not bounded above, and this implies that integral from a to infinity g dx, which is not bounded above, hence it is divergent, and hence proved. आणि अशा पद्धतीनं हा थेरम कम्प्लिटली प्रूव्ह होतो. दिस इज अ व्हेरी इंटरेस्टिंग आणि इझी थेरम. हा खूप इंटरेस्टिंग आणि इझी थेरम आहे, काही अवघड नाही आहे हा थेरम, लक्षात घ्या. म्हणजे या थेरमला प्रूव्ह करायला काही अडचण जात नाही. हा, ठीक आहे. तर अशा पद्धतीने इथं 2 थेरम आपण प्रूव्ह केलेले आहेत. आता आणखी एक थेरम आहे, दॅट इज थेरम नंबर 5. हा जरा मात्र थेरम परत एकदा पहा. हा इम्पॉर्टंट थेरम आहे. दिस इज ऑल्सो इम्पॉर्टंट थेरम. या थेरमला परत एकदा पहा. आणखी एक थेरम आहे, तो आपण उद्याला घेऊ, आणि मग हा पार्ट जवळपास आपला या थेरॉटिकल पार्ट संपतो. नंतर प्रॉब्लेम राहिलेले मंडेला घेता येतील. ओके, तर ठीक आहे. हे दोन्ही थेरम व्यवस्थित लक्षात ठेवा. बोथ दी थेरम्स आर theoretical theorems. If you have any doubt, then you can ask. तुम्हाला जर कुठलाही एखादा डाऊट असेल तर तुम्ही तो विचारू शकता. ओके, नाउ वी शॅल स्टॉप हिअर. गुड बाय.